Welcome to BE544. In the previous lecture, we have covered multiple techniques to overcome the overfitting, aiming to reduce the gap between the training and testing and validation so that both of them come close together and become a fit model. We utilize the dropout, where in the training phase, some neurons based on the dropout ratio are ignored randomly, and we utilize also data augmentation. We are increasing the diversity of the samples during the training phase, and we compared using experimental results the difference between them and which approach was better than the other when we applied them on the histopathology dataset. Today, we will introduce how to calculate the performance metrics, aiming to judge the performance of the system. If you remember, we reported some metrics such as precision, recall, and accuracy, and today we are going to understand the meaning behind each of them and how to calculate them. So, classification performance metrics are important to evaluate the effectiveness of a classification model, as they can help determine how well the model can discriminate between the different classes or categories and also provide some insights into the model's behavior. To do so, we can use something called confusion matrix. And the confusion matrix is a tool which is used to evaluate the performance of a classification model by simply summarizing the correct and incorrect predictions in a tabular format. And we also introduced that in the previous couple of lectures, where we plotted the confusion matrix and we emphasize that the aim is to get the highest numbers or values in the diagonal. But now we will understand how to build that confusion matrix, and from it, how can we calculate the different performance metrics. So a confusion matrix is n by n matrix. So if you have two classes, you will get 2 by 2 matrix, and if you have 4 classes, you will get 4 by 4 matrix. So n here reflects the number of categories. Let's assume for now that we are dealing with 2 by 2 matrix. So in that 2 by 2 matrix, you need 4 elements: true positive, abbreviated as TP, true negative, abbreviated as TN, false positive, FP, and false negative, FN. And based on those 4 values, TP, TN, FP, and FN, you can calculate the different performance metrics. But for now, what's the meaning behind them and how can we determine their values? Simply create a confusion matrix as mentioned n by n. So here we will build a confusion matrix 2 by 2. So we have 2 rows, 2 columns, like that. And your aim is to fill each cell here with a value. So to do that, you need to determine which of those are referring to the actual and which is the prediction. So here you need to say that I'm setting the columns to be the actual, where here we are referring to the ground truth, and the rows to be the prediction. And you can swap between them, but depending on your set or the swap between them, the cells inside the confusion matrix will change. So for now, assume that we have 2 by 2 and the actual is set for the columns, the predictions are set for the rows. Again, the actual means the ground truth or the labels in the data set, and the prediction here means the output of the model. So we need to determine which of those is true positive and which is true negative and so on. So simply put for each group the corresponding categories. What does it mean? Simply for the actual, let's say we have here binary because you have 2 classes. So let's say we have positive and negative, or true and false. So let's say that we are setting the first column to refer to the positive, let's say 1, and the second column to 0, which refers to false or negative. And also for the prediction, you need to set which is positive and which is negative. Let's say here the positive and here negative. And if you are talking medically, positive means that the patient got the tumor or the cancer or the disease. And the negative means that there is no disease or cancer or a tumor. So which one now is positive or negative or true or false? Simply based on what we set here and here. So For that cell, we are intersecting between 1 here and 1 here. This means that its labeled 1 has a ground truth, and the model predicted it also to be 1. So when there is a match between both of them, then this is called true. True means that the prediction matches the actual. And to determine whether it's positive or negative, it refers to the label. So 1 here means positive, so we say here true positive. So again, true positive means that the prediction matches the actual and both of them are positive. Also here, it's an intersection between 0 here and 0 here. So there is a match between the actual labels and the predictions. So it's true. And because it's 0 or negative, we are calling it here negative. So it's true negative. What about here and here? False positive and false negative. For that cell, to determine whether it's false positive or false negative, simply check the intersection as we did. It's 0 here and 1 here. This means that the model predicted it to be positive, but as an actual label, it's negative. So we call it false because there is no matching between the actual and the prediction, and positive here refers to the prediction. So false positive means that the model predicted to be positive, but in real, it's negative. Also, we call the false positive to be type 1 error. Here, when there is no matching between the actual and prediction, 1 here and 0 here, and the model predicted it to be negative, so we call it false negative. Again, it means that the model predicted it to be negative, but in real it's positive, and we can call it type 2 error. Now you can determine, depending on your swapping or setting for the actual and the prediction, which is true positive, false positive, true negative, or false negative. So for example, let's say that we got 5 cases, and here the rows for the actual, and here the rows for the prediction. Let's say we have 3 ones or 3 positives and 2 negatives. And the model predicted it for the first one to be 1, to be positive. A second is negative, positive, negative, and positive. So now, based on the labels for the actual and the predictions, we can fill those cells. Again, because it is true positive, this means that we are looking for the matches, and those matches should be positive. So we pick that and that. So now we set here the number 2. And for the true negative, we are looking for the matches which are also negative, which is this one only. So we set here 1. And for the false positive, we are looking for the prediction to be 1, but there is no matching, so this record. So here we set 1. And for the false negative, we are looking where the predictions are negative and there is no matching. So we set here 1. So the final confusion matrix is 2 to be true positive and 1 for others. And if you sum the confusion matrix, the summation should match the number of records. So 2 plus 3 is 5, and we have 5 records. Now after filling the confusion matrix, you can calculate different performance metrics. There are many metrics that you can report for your system, and for each there is a certain formula and meaning. So the first one is accuracy, and accuracy here is the number of correctly predicted instance to the overall instance. And here we are dividing the summation of true positive and true negative over the total number of the confusion matrix instances. So reflecting that on our system, we have 2 plus 1 for the true positive and the true negative, so it's 3 over 5. So we have 3 over 5 in accuracy, which refers to 60% as an accuracy. And the precision is a second metric, which refers to the ratio of correctly predicted positive instances to the overall predictions. And here we are dividing true positive over true positive plus false positive. So if we refer here to our matrix, true positive is 2, the false positive is 1, so it will be 2/3. So the precision here refers to the ratio of that positive cell to the overall predictions. The recall or sensitivity, or we can call it true positive rate, it's similar to the precision, but instead of referring to the portion of the correctly predicted positive instances to the predictions, here we are referring to the actual data. So instead of working for the row, we will work for the column. So we will divide true positive over true positive plus false negative. So it will be also 2/3. The specificity is similar to the recall, but instead of dealing with the positive, here we are dealing with the negative instances. That's why we are calling it true negative rate. It's the rate or the ratio between the correctly predicted negative instances to the actual negative instances. So here it will be 1/2, 1/1 plus 1. The F1 score is the harmonic mean between the precision and recall. So it's a ratio between both of them. And because both of them are dealing with the positives, the F1 score is also measuring the correctly predicted instances as a ratio between the precision and recall. So it's 2 multiplied by precision and recall over precision plus recall. The false positive rate is the ratio of the false predicted instances over the total number of negative instances. Also for the false negative rate, it's the ratio of the false negative over false negative and true positive. The next one is the Matthews correlation coefficient, which is usually used with binary classification, but it can be used with others, and it engages all four factors of the confusion matrix, and it's considered to be superior to the F1 score and accuracy, as it produces a high score only if the prediction obtains better results. Moreover, there are many other metrics that can be utilized other than those mentioned, and you need to pick which metric you are going to report and which metric is more important to you. Simply, for example, if you are talking medically, we focus on the metrics that engages the true positive in them, such as the recall, the precision, and F1 score. Because it's important to get a system or to build a system which can predict from the data if the patient has a cancer or a tumor or not. In some other applications, the true negative can be important than the true positive. So depending on your application, you can emphasize some metrics over others. Now, after understanding how to build the confusion matrix and based on that confusion matrix how to calculate the performance matrix, you may see that there are many varieties of the confusion matrix if you read a textbook or a research article, but all of those refer to the same thing. As mentioned, depending on your set, which is actual and which is a prediction for the columns and rows, you are filling which is true positive, true negative, and others. So simply, let's reflect on that. And for now, let's assume that those four cells are empty and we don't know which is positive and which is negative inside those cells. So here, the prediction is set for the columns, while it's set here for the rows to be actual. And for the first column is positive, the second is negative, here is positive, the second is negative. So simply depending on that set, we can determine which is true positive or true negative. Let's start by the simplest ones, which are true positive and true negative. Simply, true means the matching between the actual and the prediction. So if positive and positive, this means that it's true positive. If negative and negative, it's true negative. And for others, it checks the prediction and it will be false. So here, because the column is negative, so it will be false negative. And because here it's positive, it's false positive. Again, false positive means that the system predicts it to be positive, but in real it's negative. And for false negative, it's predicted to be negative, but in real it's positive. Now let's get another variety. They swapped the columns. So we need to determine which is true positive or true negative. 0 and 0, there is a match, so it's true. And because they are negative, so here we set true negative. 1 and 1, a match, and positive, so here true positive. Now for the other two cells, let's check the prediction. It's 1 here, so it will be here false positive. It's 0 here, so it will be false negative. Let's get this third variety. Actual here, prediction here, false, true, false, true. So get the true positive, true negative, false and false, it's true negative, true and true, it's true positive. Now for others, the prediction is here and this a true cell, so it will be here false positive. Negative here, so it will be here false negative. Now you understand the meaning behind the 4 elements. Now what about if we have multiple classes? Let's say here we have 4 classes, normal, benign, in situ, and invasive, and there is a confusion matrix for them. We need to determine which is true positive, which is true negative, and the others, false positive and false negative. And here in that confusion matrix, the rows are the actual and the columns are the prediction as determined in the header here. So simply assume it as a binary problem where the class you are focusing on is the positive and others are negative. For example, if we are focusing on our class here now, normal, then we will assume that this class is positive and others are negative, regardless if that class refers actually to be a cancer or a tumor. So here we will set normal to be our positive and others to be negative, here, here, and here. The same, this will be our positive and others will be negative, here, here, and here. So now we converted it to a binary problem. And from that, we can determine which is true positive, true negative, false positive, and false negative. So true positive means the matching between actual and prediction. So in that case, it will be 50. The false positive, this means that it's predicted to be positive, but in real, it's not positive, which is negative. So because this is our prediction, so we are looking to those 3 cells. 3 plus 1 plus 0, so it's 4, because it's predicted to be normal, but in real, they are not normal. And for the false negative, we will look for the prediction to be negative, which is here, here, and here, and in real, they are positive. So 2 plus 1 plus 2, so it's 5. And for the true negative, this means that there is a matching between the actual and prediction to be negative. So they are those cells, the summation of all of them. So now you can imagine that we are mapping between all classes to be a binary problem, like what we did here. The true positive is that cell, the false positive is that cell, the false negative is that cell, the true negative is that cell. Now you determined the 4 factors or 4 parameters for the normal class. You will do the same for others, a time for benign, another for the third class, and another for the 4th class. Let's say we need to determine for the in situ class. Again, to extract its 4 parameters, it change the in situ to be the positive here, and others to be the negative here, here, and here. The same for the actual labels here, here, and here. Now, based on that binary matrix, you can extract it easily. Or from your understanding of the meaning of true positive, false negative, and true negative. True positive means a matching, so positive and positive, so the intersection will be here, 40. The false negative means that it's predicted to be negative, so it's predicted to be negative here, here, and here, and in real, it's positive, so 1 plus 2 plus 7, so it's 10. And for the false positive, which is here, it's predicted to be positive, but in real it's negative, so it's here, here, and here. 1 plus 5 plus 3, it's 9. And the remaining cells will be for the true negative. Now you extracted the 4 elements for that class. After completing the extraction of the 4 elements for the different classes in hand in your problem, you wonder, we have multiple true positives, multiple true negative, and so on. So simply to calculate the performance matrix, you need to use one of those ways: weighted metrics, macrometrics, and micrometrics. And the difference between them is how to engage the elements of each confusion matrix for the different classes together, aiming to get a final performance metric. So in weighted metrics, you are multiplying the metric for each class by a weight. And the weight here is the number of the instances to the overall number of the data set. So it's a ratio. So you are giving a weight for each metric. And this is useful for imbalanced data sets, where the number of instances per category is different. In macrometrics, you are just taking the average of each metric. And in micrometric, you are summing the individual parts and then calculate the metric. To understand it well, let's get an example. Based on that confusion matrix, we extracted the elements of each category: true positive, true negative, false positive, and false negative. The first column refers to the elements for the first class normal, this is for benign, this is for in situ, and the other one for invasive. And those are extracted the same way that we did from a second, here and here. We are just added them as a list so that we can calculate the metrics easily. So here, let's assume that we are calculating the recall. So to calculate the macro recall, you will calculate the recall for each class individually and then divide by 4, which refers to the number of categories. In micro recall, first sum the individual parts and then calculate the recall. In weighted recall, you are multiplying each recall for each category by its weight. So let's start by calculating the macro recall. The recall is a true positive over true positive and false negative. So the recall for the normal is 50 over 50 plus 5. And the recall for the benign is 45 over 45 plus 10. That's why we condensed all of the elements as a list here so that it's in front of us and it's easy to calculate them. Let's continue. For the in situ, it's 50 over 50 plus 10. And the last one, 51 over 51 plus 4. Now calculate all of that, divide by 4. You will get around 86% for the macro recall. For the micro recall, sum first the individual elements. So sum all of the true positives. So sum 50 plus 45 plus 40 plus 51 over the same summation plus the summation of false negative. 5 plus 10 plus 10 plus 4. Sum all of that, you will get around 86.5 as a macro recall. And if you notice, this value differs from the macro recall. Now, let's calculate the weighted recall. It's similar to the macro, but instead of giving each of them the same amount or the same weight, we are replacing the division by 4 by a weight. And the weight here is the number of instances of that class to the total number of instances in the dataset. How to determine that? Simply, for the normal, to determine its weight, we check which is the prediction and which is the actual in the confusion matrix. So we say here this is the actual and sum each row, and if the actual in the column, sum each column. So here, the normal as an actual, we got 50 plus 2 plus 1 plus 2, so it's 55 over the summation of the whole matrix. For the benign, it's 3 plus 45 plus 5 plus 2 over the same number. For the in situ, 1 plus 2 plus 40 plus 7 over the same number. And for the last one, it's 0 plus 1 plus 3 plus 51. So you have now the weight, you have now the recall for that class. Multiply both of them together, you will get the recall weighted to that class. Do the same for others, you will get around 86.5. And you may wonder that the value of the macro recall is similar to the value of the weighted recall. That's simply because the dataset here can be said to be balanced. because in each class we have around 55, except that class it's 50. So when the data set is balanced, the three ways of the calculations can be very close together, the weighted, macro, and the micro. And the difference between them will appear when there is an imbalanced data set, where the number of instances per class is different. Now we need to know how to implement that using Python. So the input here will be the confusion matrix, which is n by n as mentioned, and the output will be the different performance metric. And later we will use the function confusion matrix that will get that confusion matrix automatically, where if you remember, the input to the confusion matrix was the true labels and the predicted labels. So we imported NumPy and we converted that matrix to NumPy so we can easily apply mathematical operations on them. So to determine the true positive, we are getting the diagonal, because the diagonal is the intersection between the true positive and the true negative. And the false positive is the column except the current true positive, and false negative is the row except the true positive, and the true negative is the summation of the whole matrix minus the extracted elements. So by doing that, we will extract the different elements for each category. So if you printed that, you will get a list for each element, as we saw here, calculated for each category. Now we need first to determine the macro average or the macro metric for each of them. If you remember, the macro refers to the calculation of each of them individually and then sum by the number of classes or get the average. So for the precision, we are determining the equation of the precision. For the recall, we are determining the equation of the recall, and the same for others. And because we are using NumPy array, it will be applied for each category individually. And the result for that will be another vector. For that vector, each element in it will reflect a specific category, depending on the order of the categories. So we applied here the mean value. So the mean will be the average of that vector. So we'll get here the precision. By doing that for others, we will get the macro average. If you need the micro, first sum each vector individually and calculate the metric. So for example, for the recall, we summed the true positive over the sum of true positive and the negative, and the same for others. For the weighted, we first calculated the number of samples and then calculated the weights, where it also will be a vector reflecting the weight of each category, something like that. There's the weight of the first class, the weight of the second, the third, and the fourth. And instead of using the mean function as we did here, simply we are multiplying that vector by its weights and sum the resultant vector that will be applied for each metric. When we execute it, we will get something like that. These are the components for true positive, false positive, false negative, and true negative for each category as vectors. These are the results for macro, and those are the results for micro. Those are the summation of the samples, the weights, and the weighted metrics. For example, the weighted recall here, it's around 86.5. The same here, it's 86.5. What about if we changed the example from being a balanced data set to imbalanced data set? The macro recall dropped to 78% instead of 86, but the weighted recall for the imbalanced data set became 82.84, which is a reasonable metric for the data. So this table compares between the three ways to calculate the metrics and which one to use depending on the case or the application. For example, the micro, it's suitable for balanced data sets for both binary and multi-class classification, while weighted metrics is suitable for imbalanced data sets both for binary and multi-class classification. And these are the recommendations. So for balanced data sets, you can use micro or macro. And for imbalanced data sets, you can use weighted and then micro. And for binary classification, it's recommended to use micro and weighted. And for multi-class classification, you can use macro and weighted. Now let's switch the gears to build an advanced model instead of manually crafting our CNN model or building a very simple model. One approach is to use pre-trained models. And pre-trained models means that we are using models which have been previously trained on large datasets such as the ImageNet dataset, and we use them and apply the fine-tuning based on our task. And this process is called transfer learning. And the primary benefits of using transfer learning or pre-trained models is the ability to generalize well across different tasks. There are multiple pre-trained models that you can utilize in your application, such as ResNet, Inception, MobileNet, and VGG16. Those models were pre-trained on the ImageNet as mentioned, and that dataset contains millions of images, which pre-trained to recognize a wide variety of features such as edges, textures, shapes, and objects. So simply, we can get that model, which is pre-trained on the ImageNet, and just fine-tune a set of layers from it or cascade it by a classification layer based on our task, as we are going to see in the implementation. So by using the pre-trained model, we can also reduce the computational cost and the time required to train a deep learning model from scratch. Because as mentioned, the initial layers of the pre-trained model contains valuable learned representations such as textures and objects. As mentioned, there are many models such as MobileNet version 2 and version 1, and you can get familiar with the internal structure of that model using this research article. This is another model called VGG, and there is a corresponding research article. And as we are using Keras or TensorFlow, this package provides these pre-trained models where you can import them easily and utilize in your application. You can go to this web page where you can find the different utilized or the different available models in the package. So to utilize one of those, go to script number 15, and this script is similar to number 12 that we implemented in the previous lecture. But the difference here is instead of implementing the simple CNN, we are removing it and switching it to pre-trained model. So here we created a function called pretrained CNN, where it accepts the base model, which refers to the pre-trained model, and the similar parameters to the other functions that we implemented. The rest, it checks if the base model is none or not available, or it didn't pass to that function. If not, use the default model, which is MobileNet version 2, which is available in the applications of the Keras in TensorFlow. It accepts three main parameters: the weights, and here we are saying initialize with ImageNet weights, the input shape, and whether to include the top or not. And include top means if you need to include the classification head. So we don't need to include it because we will implement ours, which will be targeted to our application to distinguish between four classes. Then we will turn off the number of trainable layers for that base model because we don't need to tune it. We need to keep the initial fine-tuned model, which was tuned on the ImageNet, and just use it to extract the features, shapes, and objects. After that, we will create a sequential model, which is our model. First, we injected the base model, and these are our layers, including the trainable ones. So we added a global average pooling 2D, where it will convert the output from the base model to a flattened one using global average pooling as described earlier. Then we will add a dense layer followed by a dropout layer with a percentage of 50% as a dropout ratio, another dense layer with a dropout layer, and post-cut the relo activation function, and a final output layer with the softmax if the number of classes is more than 2. Other than that, we would use a sigmoid with a neuron of 1 reflecting the binary classification. This remains similar to the previous function. the new thing here is how we utilize the pre-trained model in these few lines. This remains to the previous code where we got the brickheads dataset depending on the magnification and the category, and then defined the different parameters, created the generators for the training, validation, and testing, then exported some samples from each generator, and here we created the base model and passed it to the pre-trained CNN function, where this function will return the final model. The rest of the code will be similar to what we illustrated in the previous code, which is code number 12, where we started the fitting, got the history, loaded the best weights, reported the metrics, created the curves for the training and validation, created the prediction. Here we created the confusion matrix to display it as a figure, and finally at the end of the code we added a function called calculate or metrics to report the metrics for the micro, macro, and weighted, where this function can be found in the helpers file, where it accepts the confusion matrix and returns a dictionary filled with the different weighted micro and the macro metrics. Before executing the code, let's remember the output for the 4x benign categories classification using just dropout and data augmentation. And we mentioned that in both experiments there is overfitting, and the experiment of the dropout was better than the data augmentation because the gap of the overfitting here is larger, and it also executed the early stopping without reaching a good performance. Now, after executing the code for the MobileNet version 2 retrained model experiment, we will get that performance, where it also executed the early stopping when it settled to a specific performance. So here, the early stopping is executed, and the performance became better. This was a performance where the gap between overfitting was larger than 20% or 15% or more in both experiments, but here the gap reduced, where the performance for the training and validation became more than 80%, where earlier the validation was below 80 and the same for the data augmentation only was below 60. So we can say that this experiment is better when we utilize the pre-trained model over a simple CNN and the corresponding confusion matrix. And now you understand how to read that confusion matrix, and if you need to extract the elements and determine the performance metrics manually, you can do it. And these are the results for the training, validation, and testing for the benign category for the 40X. As you see, the accuracy is around 90% for the training, and for the validation and testing it's around 80, which we can say it's better but not the best, because there is still a specific gap around 10% between the training and validation or the training and testing. So the benefit of applying pre-trained models is reducing the overfitting and increasing the performance over simple CNNs or overtraining the models from scratch. And you can apply different pre-trained models and pick the most suitable one. Maybe you can change MobileNet version 2 to VGG16 and it can perform better. You have a variety of the pre-trained models that you can try and pick the most suitable one for your dataset. So, in this lecture, we have covered two things. First, how to build the confusion matrix and extract the performance metrics from it using binary classification and multi-class classification. And we implemented that for balanced and imbalanced datasets for multi-class classification, where we illustrated how to calculate the macro, micro, and weighted, and which one to use for both. Then we switch it to pre-trained models, and simply pre-trained models apply the theory of transfer learning, where the models were trained earlier on millions of images to understand how to capture the shapes, textures, and objects, and then you can utilize those pre-trained models in your application just for fine-tuning to increase the performance and reduce the overfitting.